So we're going to actually talk about the details of on-chip debug interfaces now. So the two that JTAGulator supports, JTAG and UART. And I'll give demos of each once we go into kind of the details. So JTAG is this industry standard interface that is really this low-level definition that was designed initially for chip level and system level testing during a manufacturing process. And it sort of expanded into being able to be used for programming of parts, for debugging of parts. Some vendors actually create additional vendor-specific functionality that can be communicated and controlled through JTAG. So it's become sort of this universal interface when it really started as just a very low-level specific interface to like test the connections of pins on a circuit board. What's really cool about JTAG is you can actually hijack all of the pins on a device through something called a boundary scan, where you can individually control either outputs or inputs of each pin. So if you can twiddle all of those pins, you can now potentially communicate with other things that are connected to that device that you're twiddling, which is how you can program external memory through controlling a chip in JTAG. Also, sometimes, most devices now have internal memory, so you can access internal memory through JTAG. So you can do standard programming, standard debugging. And a lot of this stuff, too, with JTAG, you can do some functionality without affecting the system operation at all. So if we're doing an ID code scan, which we'll do, or a bypass scan, the actual CPU operation, the product, is going to continue running because JTAG is sort of its own specialized part of the silicon. So it's really kind of neat. You can start working with the device while the thing's actually running. And most of the time, you won't mess anything up unless you end up doing, a debug command or programming command to halt the processor or something. But it's a very powerful interface. What's also interesting about JTAG versus a lot of the industry standard vendor-specific interfaces is you can have multiple devices connected to a single chain. So now you can have one JTAG connection on the board that connects, say, to 3 or 4 different devices on a board, maybe a CPU, a baseband for a mobile phone or something. Or it could be multiple chips within a single device. So now you look at a board and there might be two dies inside of a single package and you don't know that there's 2. But if you do a JTAG scan, you'll say, hey, wait a second, there's 2 devices there. And you can communicate with both of them. So it just makes it easy. You don't need to have multiple connections for multiple devices on the board. The vendor-specific interfaces that are out there, so Microchip has their in-circuit serial programming interface. Texas Instruments has their SPI-by-wire interface. Atmel has their ISP interface. Every vendor has their own kind of programming debug interface that they'll use if they don't use JTAG. But JTAG is just way more universal. The development environment for whatever target processor we're looking at will abstract a lot of the low-level details of JTAG, which is great. Because all the detail I'll give you in this presentation is all that you really need to care about, just to understand how we're detecting the pinout and how we're detecting the interface. But at that point, everything else is going to be abstracted. So once you find the interface, that's our whole thing, is once we can locate that interface, we can rely on the standard off-the-shelf development environment for that particular target chip and rely on standard off-the-shelf JTAG hardware that's designed to do the JTAG communication. Usually what I tell people is try to put yourself in the mindset of the legitimate engineer that designed the product. So say if we're looking on an access point, it's a Broadcom BCM 4702, I would try to find out if there's a development environment for the 4702, is there a recommended JTAG hardware to use for that architecture? And I believe that was an ARM-based architecture, so I'd probably find something that supports ARM. Because then everything's abstracted, and we don't have to worry about low-level stuff anymore. So that makes it nice. Here's kind of a fun slide. This is what happens if we get access to a target through JTAG. We control the entire thing. So the architecture is basically, it's a tiny little state machine that can execute instructions. So it's sort of like a little CPU, and we're basically shifting data in and getting data out. So it's lots of shift registers. The interface is a synchronous serial interface, synchronous meaning that it requires an external clock. So there's 4 signals that are required: data in, data out, mode select, and clock. And the mode select is what we use to go through the different states of the state machine, and then we're just shifting data in and shifting data out. There's an optional test reset pin that some target boards use to asynchronously reset the JTAG, or usually what they mostly use it for is to disable JTAG just by pulling the pin low to keep the JTAG port in reset so somebody can't just come up and attach to it. So what I'm working on now, and the version I have released right now looks for just TDI, TDO, TMS, and TCK, assuming that test reset isn't used or that it's being held high, which is also the case on some boards. But the next version I'm working on will detect reset as well. So if it is being used, we won't miss the interface. Because right now, if test reset's held low and we don't hook up to it, if we happen to miss that pin, then we're not going to detect it. So yeah, sometimes that's used, but we can actually, when we reset the tap, we could do it in a different way that I'll show you. For the test access port, which is the kind of CPU, if you will, of JTAG, has an instruction register that has to be greater than 2 bits per the spec. Usually it's like 4, 5, 8-bit wide instructions. It can sort of be whatever the vendor wants. And then for the data, so that's for sending instructions in. Then there's data registers, and depending on the command we send, the tap will enable a different data register. So there's one that's a bypass register, which is what we use in our bypass scan to detect the JTAG interface, where we send data in on TDI, and it comes out on TDO 1 clock cycle later. So it's just a pass-through. And that's useful if we want to access like the second chip in a scan or in a chain. We would use, put the first device into bypass and then go to the second one. So it's like, just passes the data along. Boundary scan depends on the number of pins of the chip. And then device ID is an optional register, but most vendors use it, and that's the other mode that we use to try to determine the JTAG interface. Because on power up, or on reset of the tap, the 32-bit device ID is in the data register. So what we could do is say, okay, let's reset the tap, try to shift data out of the data register, and if there's a 32-bit value in there that matches what it needs to be for device ID, then that's probably a good interface. I have a block diagram, which I'm going to skip. Here's the so this is sort of when you do a search for JTAG, like this is the picture that you most always see, and this is the actual state machine, and it looks really complicated, and the specification for JTAG is really, really long and really, really boring, like any other spec you read. But once you distill it down and sort of digest it, it's really not that complicated. So what we do, since we're not sure the state of the JTAG port on the target, is we always need to do a reset and get back to the test logic reset state. And you can do that by holding TMS high for 5 clock cycles. And if you sort of follow where the high bit goes, you always get back to the beginning. So we're always able to reset first and then continue with our operations. There's a bunch of instructions that are listed in the JTAG spec. The only ones that we're looking at are bypass, which is a required instruction, and then actually that's really the only one that we're looking at. There are other ones as well some are required. So bypass is required. There's a few others, and there's some that are optional, but usually those are implemented. And then there are commands. So there is actually an ID code, opcode, that's specific to some devices. So instead of just shifting the ID code out, which is what we're trying to do, you can actually send an opcode and then get the data out. But we don't need any of that stuff. Bypass is the only one, and that's required by the JTAG spec to be an opcode of all ones for the instruction register. So no matter which chip you use, if you shift all ones into the instruction register, you can enable bypass mode. And that way, we can always force the device into bypass mode, even if we don't know what it is. So I talked about protection a little bit. It is implementation specific. If you do encounter a device that's password protected, there's no gold standard of how to defeat it. You might be able to try to do some brute forcing. If there's a physical security fuse that's blown or a diode or something on the die itself, you might be able to decap the chip, repair it. Chris Tarnovsky is a good guy who can do that stuff from FlyLogic, which is now part of IOActive. There's a handful of people that are really good at doing silicon die hacking. So maybe that's an option, to physically repair that broken fuse on the die to re-enable the JTAG interface. Basically, if there's JTAG support on the chip itself, on the die itself, there's always a potential to re-enable it. And usually, even if there is password protection, bypass mode still needs to be active, because if you imagine if there's a few devices in the chain and if the first one's protected and you need to access the second one, you still need to have bypass. So we can take advantage of that. We'll still be able to find the interface, which is great, and then maybe we can devise an attack or something to try to actually defeat the protection. So there are a bunch of off-the-shelf hardware tools available, and I mentioned once we find the pinout, relying on existing tools is the way to go. There's no point in recreating the wheel with the JTAGulator. Really, all we need to do is find that interface, and we're good to go. There's a bunch of software tools, some open source tools as well. So again, if you can use the same development environment that a normal engineer would use with the chip, that's sort of the best way to go. But if you need to, you could use some open source tools as well that are designed to manipulate different types of processors and extract memory and stuff like that. So here's the ID code scan. This is one of the two methods of detecting the interface. With ID code, once you reset the tap, if there is a device ID available, it's going to be in the data register. So all we do is reset the tap and then clock out data and see if anything comes out. If it does, then we know that that's, if it matches the device ID format, which has least significant bit as 1, then that's potentially a valid device ID. And the device ID is going to vary with part number, with family, with vendor. Usually it's documented within the data sheet of the part, or maybe in a BSDL file, which are used for JTAG connections, a boundary scan description language. So usually what I'll do is, and I'll show you this when I give the demo, is when you get the ID code, if you do successfully find one, then you just do a Google search for that ID code, and it will probably come up with some website telling you what the part is, which is cool. And then you can validate and verify that you have the right one. The manufacturer ID portion of the device ID is given out by JDEC, a standards organization. So if you don't find anything online, you could at least take the manufacturer ID portion, go to their website, grab the free PDF, and look and verify that, oh, it is a Qualcomm chip or it is a Motorola chip, and know that you've gotten a correct ID code. So the way that it works is we basically go through every possible pin permutation and set what we think might be TDI, or what we think might be TDO, what we think might be TMS, what we think might be TCK, and try it. And if we get a device ID out, then we print out that result, and then keep trying over and over again. If the device ID is invalid, we just skip it. For bypass scan, what we're doing is shifting 32 bits of data in and seeing if we get 32 bits of data out. And at the same time as we're doing that, we're trying to determine how many devices there are in the chain. And so what we do in bypass scan is we basically just flush as many ones. We just send a ton of ones down the line. I think we have 32, I can support up to 32 devices, and I think I send 128 bits per device. So it's a lot of ones that I'm shifting through a chain, because we don't know how long the chain is either, right? So we have to shift a bunch of ones in to try to force every device into bypass mode. And then I send 1 0 in on TDI, or what I think is TDI, clock it, and see if I see a 0 come out eventually on what I think might be TDO. So it takes a longer time because I'm sort of shifting and I'm waiting and listening and waiting for a 0 to come down the line that might not ever show up. So it just takes a little bit longer. But as you'll see from the timing, it's really not that much longer. So that's basically the process, is just resetting the tap, performing this interrogation, and hopefully we find if we get the same 32 bits out, then we know with pretty good certainty that that's going to be a valid interface. So here's the timing. With ID code, it's pretty fast. We're actually not concerned with TDI, with data in, right? Because we're resetting the tap and only reading data out. So we're only looking for 3 of the 4 pins, so it's a lot faster, 264 permutations a second. But the problem is then you still need the other pin. You still need TDI. So usually what I'll do is run an ID code scan first to verify that there's a JTAG interface. And then once I know there is one, then I can do the bypass scan to get that, to get TDI, to get that final pin. For the bypass scan, 13.37 permutations per second. Just happened that way. Totally leet. And the reason it's so much slower is because we have to deal with TDI, and we have to shift in all of these different bits. But still, if you look at it like, I don't know, say we had 8 channels hooked up, 8 unknown test points on the board, 2 seconds to do an ID code scan. Even less than a minute for 24 channels. But then if you look over here, if we had 24 channels for bypass, almost 255,000 permutations, I think it's around a little more than 5 hours. So that's something where you'd set it up, take a long lunch break, and come back, and it would be done. And that's why you'd want to test with ID code scan first. But maybe sometimes if the ID code is not used in the chip, you have to use bypass scan first. Okay, so I'm going to give, so I have some examples first, just to show you, just so you have them on paper. The slides are available on the DVD, also on my website. The DEF CON badge, I'm going to give a demo with this one, just showing the ID code, and then I found this BSDL file that showed the pinout, or showed the format, so I could compare it. Here's one, a Linksys WRT54G. I have that here too. I'll give a demo of that one, a Broadcom chip. Another access point, a Samsung. I just wanted to put these in as reference. There's just lots of them, and I just have a handful of boards at home that I test on. Here's a CPLD, a programmable logic device that has a JTAG interface. That was kind of neat. Here's a mobile phone, Samsung SCH i910. What was interesting about this one is when, and I'm not exactly sure how this works, but when I'm powering the phone with a wall wart, with a charger, or if it's on with the battery, like if it's actually on and it shows a screen, JTAG is disabled. If I turn the phone off and I remove the power plug, then JTAG will work. So I don't know if that's like an intentional security mechanism or something where I'm not sure. So at first it wasn't working. I'm like, well, why is that? And then I unplug it and it worked. And I was like, what? That's really weird. And I did a search and there's like some phone hacking websites that have mentioned similar things. So I just don't know if it's intentional or not. But it was sort of interesting. So sometimes you kind of have to play around with stuff like that to uncover the secrets. Okay, so I'll give a demonstration of the JTAG portion now, and then we'll talk about UART next. So let's switch to the camera for a second, just so I can show the setup. Little manual camera switching action. Okay. Okay, it's a little bit fuzzy, but just so I don't have to hold things up. This so here's the JTAGulator. What I have is I'm using the screw terminal blocks, and I put a little 5-pin header in here just for the first demo. I always like to make sure the demo is going to work before I start doing other demos. So I have a little 5-pin header here, and then I have a cable connected to this DEF CON badge, which is an MC56F 8000 or MC56F 8006 digital signal controller that has JTAG. And I had designed this DEF CON badge a few years ago. This was DEF CON 17, and it just happened to have a JTAG interface. And I had brought out the JTAG pins to test points on the board. So for the demo, I said, okay, well, this way I'll just make a little cable, wire the test points to the cable, so everything is kind of hard-coded. So I'll give that demo first. I'm just going to plug that into the JTAGulator, which is ground, channel 0, channel 1, channel 2, channel 3. And then the next demo I'll actually use, I'm not going to switch back to the camera mode for it, but I have this Linksys device where I have a JTAG port on some of the pins and then a UART on other with just discrete wires. And this is normally how you would do it. You would just have discrete wires soldered down or connected up, and then you would just arbitrarily connect those to the device. So we'll do that. We'll do that next. So first, let's go back to the normal screen, and I'll have my terminal program. Oops. Okay, everyone tilt their heads. Good? Oh. Okay. so here's the terminal program. I already have plugged in the JTAGulator, and on reset, what you'll see oops. Make sure I have the right serial port. Okay, I didn't have the right serial port. So on reset, get a little header with some information. If you hit return, the command, the colon is the command prompt. So we just hit return. We see question mark, invalid command. Hit H, we can actually see the different commands that we have available right now. The first thing that we need to do is set the target voltage, target system voltage. So we're doing the CR2032 battery, so it's a 3 volt. So we do 3.0, new target voltage set. And now we'll do identify JTAG pinout. So we'll do the ID code scan first, and then we'll do bypass scan. So identify pinout, include optional reset pin. So this version of code that I'm running right now is the development version I'm using to add the new reset functionality, which I started doing last night. So we're just going to say no, because we're not using that right now. Enter number of channels to use. So I have 4 channels connected, 4 pins connected. And it says ensure connections are on CH3 to CH0, which they are. 24 possible permutations. I'll hit spacebar. And then, pretty much right away, there's the pinout. But we don't know TDI. It says NA, not available. But we see TDO, TCK, and TMS. So that's pretty cool. We can actually verify that. I believe it's the D command. So TDI not needed to retrieve the device ID. So now it says enter TDO pin. So that's going to be pin 3, pin 1, pin 2. That's what we just got from the scan. 1 device in the chain. And there's our device ID. Now the number of devices in the chain, normally I would do a bypass scan first and it would tell me the device ID. I'll do that next. But I just wanted to do the ID code. Where you can see, here's the ID code, 01C0601D. So then what you would do is go to Google and look that up and see what there is. So I don't have internet access, but I actually loaded this beforehand. So when you do that, you'll see stuff like this. Here's a BSDL file that says, information. There it is. So it's an MC56F8006. And then once you know that, then you can go and grab the data sheet of the part from the manufacturer and start reading in more and continuing down your hardware hacking path. So that's ID code. Let's do a bypass scan, which is B. No. Now you notice it says that the minimum number of pins is now 4 instead of 3, because now we have to look for TDI as well. So 4 channels, still 24 possible permutations. Spacebar, begin. So you saw it took like a slight bit of extra time. Number of devices detected 1. So that's how we know 1 device in the chain, and there's pin 0 is TDI. So now we have the full scan. And we can validate that with the test bypass. And when you hit enter, it saves the default value, or it saves the most recent value. So you don't have to keep retyping stuff. You can just hit enter to skip it. So TDI 0, TDO 3, 1, 2. 1 device in the chain. So match, pattern in, pattern out, match. And we can do it again and just hit enter for everything. And it will be different 32-bit values being set. So now we know that's the valid JTAG port, and now we can continue on with our attack. So let's do it with this Linksys WRT54G version 2. Just for fun, I'm going to disable the target voltage to 0. Target voltage off. Now I'm going to connect up the new one. Now the one thing you do need to do is make sure that you have a shared ground between the systems, sort of a reference, a 0-volt reference between the two. So you will at least need to do that reverse engineering to figure out where ground is to share. Otherwise, they're not going to be able to communicate properly. So I'm going to connect ground, and then I'm just going to arbitrarily plug in these 4 pins from this connector. I don't know what they are. Get that one to fit in there. There, okay. So now I have the 4 wires from this unknown connector plugged into the JTAGulator. And the, let's see, it's all powered on. So I should be able to now set the target voltage. I think the target voltage for the router is 3.3. But we'll see if that's right. So now we'll do an ID code. ID code scan. No, we don't want the reset. Number of channels I have. 1, 2, 3. Okay, so I still have 4. Spacebar. Yep, and then right away, so TDI we don't know, and then 1, 2, and 0. So let's do a bypass scan. No. 4. Yeah, so now we know TDI. TDI is pin 3, 1, 2, 0. So if I actually, just to prove that I'm not faking this, I'll switch some of the pins. Okay, now let's do it again. What was that? Bypass scan, oops. Bypass scan. No, 4 channels. Tabulating 2130. So it was what? 3210 or something, and now it's different. So 3120 and 2130. So it's going to work no matter, how you plug in the connections. Okay, so that's the JTAG scan. I'll go back to the slides and I'll show you UART. Okay, so this was the second protocol that I added to the JTAGulator. Originally it was just JTAG, and then this is the next thing, and I have a whole list of other interfaces. So UART is a very common interface for debug and for communicating to a device. It's an asynchronous serial interface. So when you think about serial ports, this is what it is, a UART, asynchronous receiver and transmitter. So asynchronous meaning there's no external clock, so the signal itself has the timing kind of associated with it. So you have to have the correct baud rate in order to correctly identify the data. And here's sort of a spec. You have a start bit, 5 to 8 data bits, and then a stop bit. And looking at UART data is sort of, the more you look at it, the more obvious that it's asynchronous serial versus some other signal. So if you're probing a board, you might be able to take a guess and go, oh, I think that's a UART. But in most cases, being able to automatically detect it will be easier. The most commonly used pins these days are just TX and RX, just transmit and receive. Back in the day, we had a bunch of different control signals that were used for handshaking and making sure that the systems, one system was ready to receive data from the other, and there's sort of all these incompatibilities. But nowadays, TX and RX are usually what you see. So on an embedded system, say an access point, which I'll give you the demo of, you usually see something like power TX RX ground as a 4-pin connector, for example. Even though you don't really need power, usually it's on the connector. Or other times it's not. But TX and RX, those are the ones, and those are the only ones that we're looking at. We're not trying to find these other control signals. Lots of embedded systems are using UART for debug outputs for root shells and stuff, and I'll show you an example, and I'll show you a real demo as well. So here's what it looks like if you do probe on a board and look at an asynchronous serial data stream. Just kind of looks like that. The important thing, and the way that we can figure out the baud rate, is by measuring the bit width, which is the narrowest portion of the wave, the narrowest transition. So in our case, you can see there's some small pieces. Ends up being around 8.7 microseconds. If you do 1 over 8.7, you end up getting around 115.2 kilobits a second. It's actually 114.9, which is within the standard kind of deviation or within the tolerance of RS-232 of serial for 115.2 kilobits per second. So normally we would take a measurement of the bit width and then set our terminal program to the nearest standard baud rate. And that's basically what, that's how you would manually figure out UART. But in our case, what we're doing is we're just setting up the standard configuration, 8 data bits, 1 stop bit, 8N1. And we have a bunch of standard baud rates stored in a lookup table. So all of these. It is possible for a vendor to be tricky and use like a non-standard baud rate, which in our case, since we're doing a table lookup, we might not see it. But the cool thing about asynchronous data is even though we might not see the exact data, we might still see a response of some sort. And you'll see in the demo, other like different baud rates are going to show you maybe it's junk. But at least you know that you see a signal on that pin, and then you could always go and use the oscilloscope to figure it out. So even if a vendor is trying to obfuscate it, you'll be able to find it most of the time. So the scan, what we do is we ask the user for a desired string. And normally it's just carriage return. You know, so like when you connect up to a system, you'd usually hit enter or something to try to wake up the system. Maybe you know that the system requires some other sequence, some other keystrokes. So you have up to 16 bytes that you can actually enter what you want it to send on what you think the TX pin is, and then we're going to look for responses on what we think the RX pin is, and then we try all the different permutations. So that's basically what we do. What we do as well, since we're sending a string, we're going to wait up to 20 milliseconds to receive a byte back, which is pretty long in computer time. And if you don't get a response back on that pin within 20 milliseconds, so we just assume that it's not a valid UART. If there are any bytes that received, we're going to see the first 16 bytes that the system sends back, that the target is sending back to us. And again, as you'll see, if it's not the valid baud rate, you might still see data. And then the human, you, will go through and choose the one that seems to be the most valid one, or try those. But at least you have that pin out, and that's the key. Here's an example of the UART scan. So I have a defined string, which I can't remember what it was. I think, yeah, so my defined string I think was hello, is what I'm transmitting at different baud rates. So I have my oscilloscope set up with digital decoding at a certain baud rate, and I'm trying all the different baud rates as TX. So I'm sending hello as my string to the target, different baud rates, and then let's wait until, so there's that one baud rate where we get a response back. And that's basically what we're doing, is we're just reading that receive line until we see some data. So for the speed, since we only have to locate 2 pins, it ends up being about 1 permutation a second. So 10 minutes at the most. Not too bad. I have 2 examples. So the same Broadcom, the Linksys WRT54G, the same one we just did the JTAG test on, also has a UART on a separate set of pins. So the UART, or the JTAG was here. Here's the UART. And I'll show you, I'll give you a demo of that one. Here's another example. Here's a set-top box from Israel. And a student had come to one of my hardware hacking classes and said, hey, I've heard that there's some sort of root shell interface on here, but I don't know where it is. Can we find it? So we sort of went through the process of looking on the board, identifying the interfaces, looking for the very obvious connectors, and then poking around with our oscilloscope to find out which one it was. Now, if I had the UART detection functionality done on the JTAGulator, we could have just hooked up, test points, hooked all those up to the JTAGulator and had it do it automatically, but we didn't. Once we ended up finding the correct pinout, we had to use a level shifter, which had an FTDI part on it, so a USB to serial adapter. Hook that up to a terminal program. We got the baud rate right, and then we can see it's this boot up screen with U-boot and stuff, which is pretty cool. So that was more of a manual process. I'll show you now how you can do it with the JTAGulator that is way cooler and requires just less hassle. Okay, so let's switch. Actually, no, you know what? You don't even need to switch that. You're okay. I realize I can just use the terminal program. Switch back to the slides, please. All I'm doing here, you don't really need to see this on the screen. I'm disconnecting the JTAG cables, and I have a bunch connected to the UART, which now I know is the UART, but I don't remember what the pins are or anything, so I'm just going to connect these up. So it's a 2x5 row header, but one side, I'm looking at one side, and so there's 5 pins. I have ground hooked up, and then I have 4 other pins, so I'm going to connect those to CH0, 1, 2, and 3, just like I did before. And I don't care how they go in. Let's reset the device just to be safe. Okay, so now we're in cool term. I think the settings are probably still the same. Yeah, so still we're set at 3.3 volts. So now I have things hooked up to the UART. And okay, so now all we do is identify UART, text string. We're just going to use carriage return as our text string to send. Number of channels, we have 4. 12 possible permutations. Press spacebar. Let's see if anything comes up. And you see those little dashes that were coming? That was another feature I just added to kind of show progress indicator. And then all of a sudden we get this massive dump of responses. And you can see the TX and RX are all the same. Pin 3 for TX, pin 2 for RX. But for different baud rates, we're seeing different data coming back. Now, since we don't know what type of data we're expecting back from the target a lot of times, at least the JTAGulator doesn't know if it's supposed to be printable ASCII or if it's supposed to be something else. This is where the user comes in to actually go through manually and determine if that's a likely scenario and if that's worth checking out more. So we can go through and see if we see any bytes that might be be something useful. So we go through, we see 57.6 has 0D, carriage return, right? Go down more. Here's 115.2, 0D, 0A. So carriage return line feed. That's probably the one. That's the right baud rate. So let's try that. TX of 3, RX of 2. So now what we can do, instead of having to disconnect the JTAGulator, put on a different level shifter, get your terminal program set up again and all of that, we can use what's called the pass-through mode to let the JTAGulator do all of that. So let's do P. What was it? TX pin 3. RX pin 2, baud rate 150. Not 116. That's not going to work. Cancel that. P 3 2 1 1 5 2 0 0. Sometimes I'm bad at typing. Okay, entering UART pass-through. So now we can just start communicating and interfacing directly with the device that we've just discovered the UART for. So here we go, DDWRT. I think the login is, it's not root. I think it's admin password or something. Admin password? No. Maybe root. I have local echo turned on. Root admin. Yes, I hacked it. Okay. So now we log into DDWRT, which was loaded on this access point. And now I have a root shell, and I can just sort of, manipulate the device. And now I'm in. So kind of cool. And then when I'm done, I can hit Control X, UART pass-through complete, and now I'm back communicating with the JTAGulator instead. So that is UART detection. So there are some limitations. Like any tool, sometimes tools are good for certain jobs, sometimes they're not, sometimes the tool isn't going to work. So there are some limitations. One of them might be that there is no on-chip debug interface for that target. Maybe the device is physically disconnected, like we talked about. Maybe there is a reset pin being pulled low to disable JTAG. What we have right now with the current firmware that's available on GitHub and that's on the units, I basically, any pin that we're not currently manipulating, any channel we're not currently manipulating, I have set high. So if there is a reset pin, it's going to keep it high, so it's going to enable it. So the system, you'll still be able to detect the interface. But eventually, the next version, they're all going to be low, and then I'm going to try to set it high only to discover if there is a reset pin there. Maybe it's password protected, maybe it's some other configuration we don't know about. I'm sure there's lots of different edge cases of different parts that don't work. But my goal is to try to eventually fit those in and get feedback from people that are using the device. I have a list on GitHub of known good targets. So as that list grows, people will be able to know if there's a special thing they need to do. Maybe there's strong pull-up resistors that are preventing the JTAGulator signals from being the proper levels. One limitation, which is only a limitation sometimes, is that possibly as you're fuzzing this interface, you're sending different data streams on different pins of test points that you don't know what they are. You might end up causing the device to operate abnormally. But from a hacker point of view, if you can cause some sort of issue to happen, like that might be another clue that you can then use for another hardware hack or something. So somewhat of a limitation, but if you use it right, it could be useful. Some future work, I mentioned I have lots of stuff to do. This list keeps growing. I want to do lots of different interfaces. Flash memory devices, you can even communicate directly to those and get information back from them about their memory size and configuration. So now we might be able to detect if there's a flash memory device on a board, which I thought would be kind of neat. Possibly doing a level shifting module to allow adjustable target voltages above 3.3. So for industrial equipment, SCADA equipment, there's lots of stuff out there that's still 5 volt and above, especially for UART interfaces. Maybe do a logic analyzer. Since we have 24 channels with proper input protection, there's no reason why we couldn't write some code to just read the state of whatever pins that we're connected to and then interface it with something like SIGROC, an open source logic analyzer tool. That would probably be done in assembly language on the chip, so you can get kind of maximum speed. But I think that might be cool. Since you're already, if you already have one, it will sort of prevent you from having to buy another logic analyzer. So lots of stuff in the future. If you want to get information, all the stuff is available on JTAGulator.com, which just links over to my website, which is Grand Idea Studio. So schematics, source code, bill of materials, test procedure, everything you need. Gerber plots, if you want to send those to a local PC board fabricator, you could do that. Everything's online, and then from there, there's a link to the firmware on GitHub. Parallax, I mentioned they manufacture the units. So they sell assembled units, and they sell, I believe they have the Bus Pirate probes, and they currently sell bare boards. I think they have maybe like 20 or 30 bare blank PC boards left for $20. So if you wanted to buy a bare one and build your own, you could do that. OSH Park is a guy out of Portland named Neil Lane is his handle, and he fabricates circuit boards for the hobbyist community and basically batches and copies everybody's designs onto a giant circuit board panel and then gets that fabricated because the cost of board fabrication is really determined by the size of the panel. So if you only have a tiny little part, you might still have to use their minimum panel size. So what he does is batch everything together, and so you wait a few days longer, but now you pay some few dollars per square inch to get your boards back. So I uploaded the designs to there as well, so you can always order from him. So we have about 15 more minutes in the presentation. So what I'll do is I guess we'll open up for questions, and then feel free if you want to come up and experiment. We can use my machine. I have 2 JTAGulators here. I have a bunch of different target boards. I have a BlackBerry device and another access point. I have a logic analyzer. I have a bunch of stuff. If you want to come up and experiment and kind of play around with the technology, feel free. And then, we'll just do that until we're done. So any questions before we kind of open it up for the hands-on? No? Okay. Well, thanks for coming.